Okay, great. Today, we're going to be talking about a topic which has been around for several years at this point, but it's still a slippery topic. A lot of people want to know whether they are affected, and if so, how big of a deal is it, and what can you do about it specifically? This all stems from a paper that came out back in 2016 by Anders Eklund. But before we start talking about that, before we start talking about their methods and what it applies to, I'm going to give a more conceptual background because this goes beyond just fMRI data. And I'm going to start with a paper that was published back in 1988, way back in the 20th century, which seems crazy to say now. But this is a classic study, very, very good paper, very well written, by Elvin Feinstein, called The Scientific Standards in Epidemiologic Studies of the Menace of Daily Life. And I think the phrase menace of daily life is a stroke of genius because we always come across this. You've come across this in magazines or online popular press. They always have new studies coming out looking at huge cohorts of individuals, thousands, tens of thousands of people sometimes, looking at all different kinds of variables. Do you smoke? How much red meat do you eat? How many friends do you have? How much do you exercise? And even back then, this is going on 30 years, Feinstein pointed out that a lot of these huge studies that have so many different variables can cherry pick and find nearly any kind of different correlation that they want. And this really hasn't changed today because now we're being bombarded with things like if you drink 2 glasses of alcohol a day, how much does that increase your risk for lung cancer or prostate cancer or what have you? And he was specifically in this paper focusing on 3 separate, really large-scale studies that had contradictory findings. And they looked at things like, I think, alcohol consumption and breast cancer, and coffee drinking and prostate cancer. And just as we find today, especially in our field, he pointed out that a lot of these results are finding are both hypothesizing after the fact, or after, say, results are known, and also they seem to be uncorrected for multiple comparisons, which is a theme that runs into the Eklund cluster correction paper. And what's always a source of amusement to me is no matter how many of these really large-scale epidemiologic studies that we come across, they always seem to come to the conclusion that if you seem to get moderate amounts of exercise, you get enough sleep, you eat relatively healthily, you have a few close friends, you have good relationships with your family, you're probably going to be pretty healthy, just in general. And it seems to be always this kind of surprise after they do these massive studies. So how does this relate to fMRI data? We're getting closer to the present day. And back in 2009, there was a very famous study published by a researcher named Bennett and his colleagues, which illustrated the problem of multiple comparisons, which is particularly problematic for fMRI data. What they did, you may have come across this. This was one of the first papers I read right when I started doing fMRI analysis, was they put a dead salmon into a scanner. Poor guy, I'm sure he had a good life, but they put him in the scanner. And just to clarify, this fish is deceased. There is no brain activity whatsoever. And they showed the fish IAPS photos, which are photos designed to elicit very strong emotional reactions. They could be very disgusting photos. They could be very disturbing photos. They could be very happy photos. Anything from somebody pointing a gun to an older couple snuggling, something like that. So designed to elicit different kinds of emotions. They showed this to a fish, and they did the analysis just like you would do with a normal human subject. You would do smoothing, you would do, co-registration, motion correction, and statistical analysis. What they found was if you do, I forget the exact contrast, this might be like disgusting minus happy photos, something like that. Regardless, you find a significant effect in the brain of the salmon. This is the brain right here. And they get a couple of voxels, and they pass their threshold of 0.05. Now, obviously, this result is spurious. It's impossible. We know that a dead fish is not having some kind of brain response to these different photos. But nevertheless, it illustrates that no matter what, you will get some false positives. And why is that? Well, just like with these massive epidemiologic studies, we have many different tests in an fMRI data set. Typically, when we acquire these fMRI images, they're gigantic three-dimensional cubes composed of much smaller cubes. It could be thousands, tens of thousands of smaller cubes called voxels. If your resolution is low enough, like say 2 by 2 by 2, it could be as high as 500,000. And this is important because even if you do things like smoothing, you assume that they all aren't independent of each other, there's still tens of thousands of tests that you need to correct for. And this is statistics 101. You know that if you do multiple tests, you're going to inflate the probability you're going to find a significant result just due to chance. And we have this problem on steroids in fMRI data because we have so many thousands and tens of thousands of tests that we need to correct for. Now, the easiest way to do this is a Bonferroni correction. So it's simply the number of tests you have divided by your alpha level. But are all of these voxels independent? If I give you a typical slice of an fMRI data set, let's say this is a sagittal image through an fMRI image I collected. If I zoom in on a subset of these voxels, let's take a closer look at these. Highlighted in rectangle A, let's say at the center of this rectangle, this middle voxel here, I don't give you any information about it. All you know is that the surrounding voxels have these values, right? So the intensity reflects some value. It could be, I don't know, some arbitrary bull signal that we're collecting, where higher corresponds to brighter and lower corresponds to darker. So knowing all this, the values are relatively dark, they're relatively low, and you would be entitled to make an educated guess that this center voxel is also going to be relatively dark. You're not going to be perfect probably in your guess, but you're going to be in the ballpark. Likewise, if I focus on something like rectangle B over here, and I don't tell you anything about the central voxel, but everything around it, you would say, yeah, some are a little bit darker, some a little bit lighter, but it's in general lighter than this rectangle over here. I'm going to guess that the central rectangle or voxel is pretty bright. The intensity is relatively high. And again, you would be in the right ballpark. So what this means is the voxels are not independent of each other. Knowing things about the neighbors tells you something about the central voxel, and that amount of information or correlation with that voxel tends to taper off in concentric circles as I get farther and farther away. That should make intuitive sense because we know that certain patches of cortex tend to share certain characteristics with each other. They tend to be anatomically and functionally similar, such as visual cortex, for example. What this means is that Bonferroni correction is too severe. And although doing something like that virtually guarantees that you'll never get above a false positive rate of 5%, in other words, you're not going to be finding false positives, it does really inflate the chance you're going to commit a type 2 error or a false negative, meaning that you're not going to say that there's any significant results when in fact there probably are. Now, which one is worse is up to you. In medical fields, type 2 errors seem to be relatively more severe because if you don't say that somebody has cancer, for example, but they do, that can be a real problem. If you do say they have cancer, they might undergo some treatment that obviously is not great for them, but it also, the trade-off is really up to the practitioner. So there's a balance between all that. Now that brings us to clustering. So because we know these characteristics of fMRI data, because we know that there isn't complete independence between them, we take advantage of that fact and we can use a different type of comparison correction. This was a survey carried out by Tor Wager's group. This is Wu et al. 2014. And this was a literature survey, I think through PubMed. They found that the overwhelming majority, about 3 out of 4 studies, 75%, use something called cluster extent thresholding for multiple comparisons correction. A smaller proportion, say voxel-based, that gets into what I call Bonferroni, for example. It's where you're looking at each individual, and let's say you're dividing your 0.05 nominal alpha threshold by the total number of voxels that you're testing, which, as we've seen, is probably too conservative. But still, it's valid. There's nothing wrong with it. You will, in fact, be reporting results that probably don't have false positives, and about 1 in 5 studies report that. Now, uncorrected, think back to that Salmon paper. They didn't correct for any multiple comparisons whatsoever, either voxel-based or cluster extent thresholding, and these are typically not seen as valid. There is a time and a place for it sometimes. There's a debate about whether you should include them at all. Some people, if I'm just investigating the data a little bit and I'm making all the disclaimers about how it's not corrected, I should be able to show it just because it may show some trend that's worthy of future investigation. I'm not going to get into that. My own preference is, if you do want to have the disclaimers, obviously, don't do any kind of population inference, and maybe put it in a supplemental material section. In any case, so this was now 7 years ago, and I haven't seen an update on this breakdown since then, but my guess is the proportions are still the same. Cluster extent thresholding seems to be the dominant mode of multiple comparisons correction. Now, we're going to get into the mechanics of cluster thresholding in just a second, because now back in 2016, a paper came out about this very type of thresholding. So a lot of people, like I've said, 3 out of 4 roughly, they use cluster extent thresholding, but this paper looked at how that was being conducted. This is the famous, or infamous, depending how you view it, Eklund et al. Paper. And here's the key phrase. It's taken from the first paragraph from their significance statement. And I quote, "We found that the most common software packages for fMRI can result in false positive rates of up to 70%. These results question the validity of some 40,000 fMRI studies." Now, something as explosive as that was obviously picked up by the popular press. This is just one example, The Economist, and the headline kind of says it all. And this was across many different mass media publications. This is a big deal because we're giving out multi-million-dollar grants every year, very big studies, very big longitudinal studies using fMRI, which is not cheap. It's time intensive, it takes a lot of money. And if it truly is invalid for such a large proportion, I mean, basically the vast majority of papers ever published with fMRI, then that's a problem. Just a side note, this is not the first time that we've had people criticize the methods used by fMRI. There's been criticisms of double dipping, using the same significant ROI for future analyses. There was a so-called Voodoo Correlations paper by Equitable and colleagues. Even a paper looking at how interactions were reported by neomice. This last one, I'm sure we're all kicking ourselves because it simply said things like, if one condition is statistically significant, the other one's not statistically significant, that does not necessarily imply that the contrast between them is statistically significant. And it was a Nature paper, which seems like really low-hanging fruit. But these types of things were being done often enough, especially in fMRI, that it merited these kinds of papers. So it's not the first time, but the Eklund 2016 paper was, let's say, an order of magnitude more serious than that. So for the rest of this talk, I'm going to be unpacking this. First of all, is it true what they said? I should point out that Tom Nichols did issue a clarification qualifying that first statement that I showed you before, because in fact, it was the absolute worst simulated scenario that they came up with, which seems a little bit irresponsible to make the focus of your significance statement. So they did do that. It was, a week or two afterwards when there was a big blow up about it. But regardless, the damage had already been done and most people didn't see it. Second, how big of a problem is this? So if it does indeed affect you and the data that you're working with, how severe is it, and what, if anything, can you do about it? So like I said, what were they criticizing exactly with cluster thresholding? We'll talk a little bit about that, how it works, the problems that they pointed out with cluster thresholding, and lastly, how to address these problems. Now, we will be doing this in AFNI. Having said that, think of this as a template because the AFNI command we'll be using, 3D can also be used with the output of SPM and FSL. Once this workshop is done, I'll send around the script that we've been using and pointing out what exactly you need to fill in if you have, say, your SPM contrast maps or your FSL contrast maps. So yes, the focus is on AFNI. We had to choose one, but it can be applied to any of them. As we said previously, not all voxels are independent. And the correlation between voxels tends to be very high for the surrounding voxels, and it tapers off as you go farther and farther away. That's just due to the intrinsic nature of the brain, and also, more importantly, because of one of the pre-processing steps that's done on nearly every fMRI data set. This is spatial smoothing. If I have my original data set up here, okay, this is my fMRI image, no smoothing has been applied. Now I can apply something called a smoothing kernel of different sizes. And as the size of this kernel gets bigger and bigger, the amount of spatial smoothing also increases. Excuse me. This is an example with 4 millimeters, and then 8 millimeters, and then 15 millimeters. The reason this is done is, one, we're taking advantage of the fact that voxels and their neighbors are not strictly independent. If there is indeed signal at one of the voxels, it's probably going to be shared with its neighbors as well. Then if you take the smoothing, you're going to be averaging across that signal. And if there is indeed noise, we assume that the noise is a random fluctuation around zero, both positive and negative. You average those together and it should cancel out the signal and it should boost the noise. The drawback to this is, obviously, as you can see, the spatial information tends to get fuzzier and fuzzier as your smoothing goes up. Most kernels are within the 4 to 8 millimeter range. When you finally run your statistics, this has the benefit, like I said, it can increase your signal, and it will also increase the size of the clusters. Notice, however, that there seem to be limits to how beneficial this can be. If you have a very, very large smoothing kernel, 15 millimeters is starting to get on the very extreme side of it, you will start to smooth across functionally heterogeneous areas. And also you can start to smooth across different tissue types like air or the ventricles or white matter, unless you've, say, masked those out. But in any case, there are limits to it. It's not as though you can indefinitely increase smoothing and keep getting beneficial results, which is why I said it tends to stay within a range of about 4 to 8 millimeters, typically. Now, when we do something like cluster extent thresholding in apnea, so I'm going to narrow down the focus to apnea at this point. The smoothness of the data set is going to be estimated from the residuals. What does that mean? When you run a first level analysis, you're including all the conditions and all the covariates that you think might explain the signal that you're seeing. This creates what's called an ideal time series, and anything that deviates from that is a residual. We make the assumption that that is basically noise. Anything not picked up meaningfully by one of the conditions, that's being modulated by one of the conditions, we assume is noise and is a residual. The way this used to be done in apnea was through a command called 3D full width half max. So let's say you give it a mask to restrict it just to the brain, and then you would give it one of these residual data sets. So ERRTS is typically how you would specify something that is an error time series. It's noise, it's the residuals. And you would get something like this. These are the smoothing parameters in the X, Y, and Z directions. Sorry, something happened outside. I'm briefly just going to mention that in older versions of 3D full width half max, it would give you, the estimated smoothness. In newer versions, anything that's post 2016, post the Equitable paper, you would get these new values. So what exactly are they? Hold on, I'm gonna jump ahead briefly. Now, when you would use that type of when you'd use that type of smoothness estimation, this would give you an estimate of how big you would find certain clusters due to chance. But in the Equitable paper, they found that if you use this older version of apnea, you would get false positive rates, which is on this y-axis right here, of very, very high rates. So it could be anywhere from 10 to 50%, much larger than the nominal rate of around 5%. The way to read these graphs is you have the nominal 5% false positive rate in black right here, and then a certain confidence threshold around that. So we're not expecting our cluster correction mechanisms to be perfect and around 5% every time. You will find some variation around that, but you shouldn't see it more than these gray dashed lines. Now notice that they're using all the different major packages. So there's SPM, there's FSL, Flame is part of FSL. Then there are a couple of different methods from apnea. So 3D t-test and 3D MIMA are a couple of the big ones for doing first level analyses and second level analyses. Notice that these false positive rates seem to be very, very high. And just by the way, how they came up with that 70% was if you look at the different simulations that they did. So here you can see where they have the most extreme outliers. Their one simulation that seemed to be above 70%, that was the one that they used for their significance statement. So just right off the bat, this does seem to be an exaggeration on their part. It's not as though they didn't have a valid point that there were inflated false positive rates, but it's not as severe as it was being made out to be. So regardless, you're still seeing pretty high false positive rates, but I also want to qualify this a little bit, because if you look at it from different voxel-wise thresholding levels, say 0.01 or 0.001, your false positive rate goes down quite a bit. So if your initial screening threshold is about 0.001, and then you use 3D ClusSim, your overall false positive rate is actually pretty close within the bounds of being around the false positive rate that you would expect. If, on the other hand, you use something like voxel inference, which is in this upper right panel here and this lower panel here, notice that the false positive rate is actually too conservative in a lot of cases, especially for SPM and also FSL. The major point of their paper is that if you don't use AFNI's traditional 3D ClusSim method, and instead you use permutation tests, which is indicated by perm, in all these different cases, permutation seems to give you the correct false positive rate. Not surprisingly, Anders Eklund developed one of these permutation software packages called Broccoli, if you want to do a non-parametric randomization of your results and build up a distribution from there, and not make an assumption about normality. So knowing that the false positive rate depends on certain parameters, let me go back a couple of slides. Remember that we had a command to estimate the smoothness of these noisy data sets. And then you would input this smoothness estimate into something called 3D ClusSim. You'd give it a mask to restrict it to brain voxels. You would specify what the smoothness seemed to be in millimeters. And you would specify two more things. You'd specify this A threshold or alpha threshold. Our nominal threshold 0.05, usually that doesn't change. And then a P threshold, which is your voxel-wise threshold or cluster defining threshold. It would then generate a table. It would say, a certain percent of the time I see voxels, or I see clusters of this size or greater with this particular cluster defining threshold. And then you would look at your results and you would say, okay, I have these clusters right here. They're all above that threshold of 668 voxels, and I'm entitled to go ahead and say that yes, these are indeed significant clusters. At this point, I'm going to break out of the slides, and this is kind of self-promotion, but also something that will help. This is Andy's brain book. Again, a link I'll be sending out after this is done, and there is a chapter here on cluster correction. Now, it recaps a lot of what we've talked about so far, but there is an animation I want to show you, which I hope will clarify some of what I've said so far. So first, I'm going to mute it, and then I'm going to go to what this cluster defining threshold is, because I've been throwing that term around quite a bit. So, and just for the record, this was done in FSL, but same concept. Let's say that you run your study start to finish and you get a result like this, right? And you're making it look all nice and pretty. You have positive and negative. If I'm going to focus on a single slice like this one, notice that, just eyeballing it, I can roughly divide this into different clusters. So different patches of voxels that seem to hang together, right? Now, if I look at this at a slightly different perspective, if I look at this like topography, and there are mountains and valleys, at the very top, in brighter, more intense colors, are more significant voxels. And bluer, more dark blue, lower ones are negative voxels. What we typically do is we set something called a cluster defining threshold. What that means is if I have something like a cluster defining threshold of 0.001, which corresponds to a Z value of say 3.1, same thing, I'm only going to show these voxels right here. So these clusters that hang together. And this is called the cluster defining threshold. Just to confuse you, this is also sometimes called the voxel-wise threshold, right? So if you use SPM, that's the thing you specify for your uncorrected value. In AFNI, as a result of that slider bar, as it goes up and down, you see the uncorrected p-value change. That's your cluster defining threshold. And in FSL, that would be something like this Z threshold that you specify as part of your post stats. So what happens once we have that? Now, the cluster defining threshold is not the alpha level. If you didn't do anything after that, that would simply be that uncorrected threshold that we criticized earlier as part of that salmon paper. Instead, what we're going to do with AFNI's 3D full width half max, remember that gives you the estimate of the smoothness of the residuals. Okay, now you already have your result, right? But what if you created a synthetic data set that was the same size, same number of voxels as your results data set, and the same smoothness of your noise residuals? How often would you see a cluster like that or larger simply due to chance? So let's say I create one of these synthetic data sets. Oh, sorry. So let's say my result initially was 50 voxels. So that's what I've gotten to start to finish. How often would we expect a cluster of that size due to chance? We're going to run a bunch of simulations. This is what is happening under the hood with 3D ClusSim. So these are artificial data sets, same dimensions, smoothness. It's a task data set. And let's say I create one of these and the largest cluster is 39 voxels. I'm going to set that aside, run another simulation. Largest cluster, just due to noise, due to chance, 52. And I keep doing that over and over. Eventually, we're going to build up a distribution of these noise results because we're still going to get significant cluster sizes. And I do that enough times, I build up a distribution. I note that the cluster of the task data set was 50. How often do I see that in my noise distribution due to chance? And if my initial result was larger than that, I go ahead, reject the null hypothesis, and say that it's significant. So I know that was a lot. At this point, I'm just going to ask, are there any questions, any clarifications about that particular method? Because it has a bearing on everything else that we're going to do. Okay. So back to the slides. So we've already covered, Equin basically criticized every major software package using their default, cluster correction methods. He says, permutation testing seems to do pretty well. Okay. So this was what I call the old method of AFNI that they were criticizing. And Equin had some very valid criticisms because there are problems with cluster thresholding. So, oh, sorry, I think there's a question. But anyway, we'll get to that later. Cluster thresholding assumes that 1, spatial smoothness is constant over the entire brain, and 2, spatial autocorrelation is normally distributed. The second point is what Equin was really focusing on. So 1, smoothness does not, in fact, stay constant over the entire brain. It's actually varying, and it tends to be a little bit bigger in things like the midline regions. So think about this, especially those of you who mainly focus on things like the medial prefrontal cortex, and I did a lot in my postdoc and graduate school years. Lo and behold, you tend to get pretty significant results with most studies in the MPFC. It could be that that region truly is involved in a wide array of different kinds of processes, but it could also be a function of how much the smoothing varies across the brain. When you look at the midline of the brain, and you take, say, a voxel that's right in the midline, and you do a smoothing kernel around it, you're going to be smoothing across both sides of the medial wall. If you're doing smoothing on the surface of the brain, you don't have that same kind of environment, and the overall smoothness is going to be a little bit less. The second assumption, which doesn't seem to hold most of the time, is spatial autocorrelation used to be modeled as simply a Gaussian. So in green is how it used to be done, how it used to be modeled with older versions of AFNI. it would assume that if we're starting at the very center voxel, right, the correlation of that voxel with itself is going to be 1, obviously. The farther away that we get away from it, radius in millimeters is down here, you're going to see the autocorrelation, the correlation of those voxels with the central voxel is going to be tapering off. And it used to be assumed that this would taper off in a Gaussian fashion. What Eklund pointed out, and this was the crux of his paper, is that it's actually better modeled as a mixture of Gaussian and exponential distributions. So if empirically we see that the autocorrelation function, or the correlation between one voxel and its neighbors, tends to go in a line like this, highlighted in black, it's best modeled as a mixed model, which tends to track it very well. The major problem with the Gaussian assumption is that the tails of the correlation are actually much thicker. They're much wider than we used to think. There's more correlation between in the brain than we thought. And what this means is that correspondingly, we're going to have to assume that there are going to be larger clusters in order to reject the null hypothesis. So lucky for us, if you've been using AFME or updated it since, I'd say 2017, I mean, just update it after this is done just to make totally sure, pretty easy to do. They have mostly, they fixed a lot of these bugs that happened as a result of being pointed out in the Eklund paper. So before, this is the pre-bug fix. There were a couple problems with that cluffsum command, including the fact that they assumed that the correlation function was a Gaussian. After they fixed it, it didn't make a huge difference, but modeling it as a mixed model of Gaussian and exponential made it a little bit closer to the true false positive rate of 5% down here. And notice on the left, this is your cluster defining threshold. As you go from, say, 0.01 to 0.001, you're zeroing in on a much more precise false positive rate. So in this bottom right corner. This is why these days, a lot of people as a default are going to be selecting a cluster defining threshold of 0.001, regardless of what software package they use. Okay. So the solutions to this are: 1, use voxel-wise thresholds; 2, use more conservative cluster thresholding; or, as we'll see later, use non-parametric methods such as permutations. Now at this point, we're going to be doing our first thing together from the terminal. So if you could, open up your terminal. I'm going to increase the font size to make sure everybody can see this. And this is within that GSU cluster failure folder that everybody should have downloaded. If you don't have it, don't worry. Again, this is being recorded. You will be able to follow along with the steps. There are a lot of files in this folder. What I want you to focus on right now, if you downloaded the latest version, is go into this directory called residuals. So I'm going to type cd residuals. First, I just want to point out, how people used to do cluster correction. It's still valid. This is still a valid approach. You can still do this. What we're first going to do is we're going to estimate the smoothness from the data, from the residuals, rather. Okay. So I hope this is, let me see if I can side by side here. The command we're going to run is 3D full width half max. We're going to be giving a mask called mask group, and then the error time series. So here's what it should look like. 3D full width half max, dash mask, mask underscore group, and then ERRTS dot sub 01 plus TLRC. So if you press enter, again, I'm using a later version a more recent version of just the APNI distribution in general. And unlike previous years, it's not going to give you simply, I'm sorry, I'm getting a message here, CPU usage is high. That's fine. Don't worry about the error. I mean, it's already been written, so it's not going to overwrite it. What I want you to focus on are these three values right here. These are these autocorrelation function values. And if you use these, you can build that mixed model of Gaussian and exponential distributions that they referenced in the paper. Okay, and they give, I don't have the equation with me right now, but these are basically parameters that have been estimated, and then you can input them and it will create a very valid autocorrelation function. This last value right here is the overall estimation of the smoothness of this noise data set for this subject. Now that we have that, we have these autocorrelation functions. We're going to be using 3D ClusSim to then estimate what the cluster size has to be to pass statistical significance. And so you're going to be giving it those autocorrelation function parameters through this -ACF option. Right? So I'm simply going to copy and paste these. And what else do I need? Right, A threshold and P threshold. So again, A threshold or nominal alpha threshold of 0.05 or 5%. And then P threshold, let's make this 0.001. Let's assume that we're doing a cluster defined threshold of 0.001. So in other words, every individual voxel has to pass this individual threshold. And we're going to be looking for clusters of voxels that are composed of individual voxels that are all passing this same cluster defining threshold. And now it's running those simulations just as we saw over here. So as this is running, this is what is happening under the hood. It's calculating a bunch of different simulations with this residual data set, and then we're going to build up a distribution. Okay, let me see if I can access the, whoops. Sorry, I can't access the chat box. I know that there was a question. If that person wants to ask now, feel free to. This is going to take just 30 more seconds or so. Okay.
Hi, Andy. It's Jeff Malin. That question was actually me. I was just wondering if you might be available afterward to answer questions on the Slack channel. Sometimes we've done it in the past with other speakers. If attendees have questions about what you're going over today.
Sure. Yeah.
Okay, great. Thank you.
Yeah, absolutely. I'm thinking we should be done by 11:20, 11:30 at the very latest, which is what we budgeted for. And then yeah, I'd be happy to answer questions afterward. So.
Great, thank you. And I see there's another one here as well. So there's a question that says, if I understand correctly, the cluster defining threshold is based both on the p-value as well as the voxel extent. Would you mind answering that question?
Yeah, the cluster defining threshold is just on individual voxels. The actual cluster extent is something we're going to be estimating using 3D ClusSim. So yeah, later on, we'll be opening up the APNI GUI. This is going to be the next and last part of the talk, I believe. And we'll see how we first set that cluster defining threshold, and then we eliminate all clusters that are composed of, say, a certain number of those voxels or fewer. So we only see clusters of a certain size or bigger. It's kind of a mouthful, but it should become more clear as we actually use the APNI GUI to set those two parameters. Okay. So going back to what was output from 3D Custom, you should see something like this. So a bunch of different tables. And let me just break it down because there's a lot going on here. It can be somewhat overwhelming at first. What it is showing is different cluster sizes. So anything, say, above 9 contiguous clusters at 0.001 individually is going to be significant given these assumptions. Bob Cox, the developer of AFNI, is always very thorough about these kinds of things, and he just leaves it up to the user to use their best judgment about what to do. NN stands for different kinds of nearest neighbor criteria. NN1 means that we're only going to accept voxels as part of the cluster if their faces touch. So imagine you have 2 cubes. I'm only going to say that they are actually connected and part of the same cluster if the faces are touching one another. Okay, so that's the most conservative criteria for defining a cluster. If instead you say NN equals 2, that means that either the faces touch or the edges touch. So it's a little bit more liberal, and the most liberal of all is NN3, which means that they belong to the same cluster if the faces touch, the edges touch, or just the corners touch, which is how you sometimes get these, long, say, threads of voxels that tend to connect different clusters. Up to you. Obviously, the more conservative ones are seen as a little bit more rigorous, but you can see here that there's not a whole lot of difference between them. Either you'd be using a threshold of 9 in the NN1 condition, or I would always round up just to make sure that I'm getting the correct false positive rate, or a voxel, a cluster size of 10. So not a huge difference. And the other thing is either going to be one-sided thresholding or two-sided thresholding. What that means is either the cluster is composed of just positive or just negative, as in one-sided thresholding, or it could be a cluster that is composed of both positive and negative values. That tends not to happen very often, and we're usually not interested in those. They're just included for thoroughness. And you can go through this and see how different combinations lead to more conservative or more liberal thresholds. For my own part, what I typically like to do, again, this is just me, I typically like a nearest neighbor of 2. Let me see if I can find it. Nearest neighbor of 2 with two-sided thresholding. That's just me. Again, you're given every possible combination. So what does all this mean? Let me scroll back up here. I apologize if you're kind of getting vertigo from this. But what we found here, these ACF functions. So this is how it was done until pretty recently. And the last part of the talk is the latest iteration of some features in AFNI to further correct for this. These ACF parameters, right now, we've only done it for one subject. What you want to do if you're doing something like a group analysis, you would run this 3D full with half max for every subject in your study. You would then take the average of this parameter, and this parameter. So like if you have 20 subjects, you would take the average of the 20 subjects first parameter to get one number in the leftmost column, same thing here, and then you would use those averaged ACF values to run with 3D Custom. Perfectly valid. If you do that, you will get a relatively stable false positive threshold that we saw in this slide over here. So you'd be looking at something down here. One more clarification I'm going to make, just because I know that there's a lot of information on these graphs. One more thing just about the Equitable paper. What kind of data were they using? They were using resting state data from, I think, Cambridge and Beijing. There's these 2 major repositories. And they ran simulations where they made it look like a block design with a certain interval of the blocks and the space between them. So two different kinds of timing paradigms for block and also for event-related designs. This is what the different clusters mean. So depending on whether most people these days, I would say, use event-related designs. If you use that and you use a cluster-defining threshold of 0.001, and you're using the most recent version of AFNI, you will most likely control for your false positive rate. You should be okay. Okay, so we already went over this. And we're now going to talk about some non-parametric options, because that's also becoming more and more popular these days. You may have seen this if you're an FSL user. There's randomize, which makes no assumptions about the normality of the data. It simply uses the data it's given. It swaps things like the sign of the values in different voxels to create a distribution from the data. It doesn't necessarily have to be normal. And then from there, it takes the 5% most extreme values and it compares that to your original contrast of, say, it could be within groups contrast, between groups contrast. And then you use that to determine whether the result is statistically significant or not. Same thing with SPM's SNPM, statistical non-parametric mapping. Now, what we've seen so far is a way to estimate smoothness from each individual subject in the study. That's at the first level. Okay, it can be kind of tedious. It does, in fact, work though. If you want something more recent, something that seems to, in all cases, control for false positive rates, there is a new option, 3D t-test ++ called dash +sim. And this is going to be another kind of hands-on practical thing that we'll do, and we will use the AFNI viewer for that. What this will do is it is going to use, it's done at a second level. So you have each of the individual subjects contrast maps that you've used. It's going to fit a model, and then it's going to use the residuals from that model, from the second level model, as opposed to residuals from the first level model that we just used, in order to run permutation tests about whether your result is significant or not. And it's going to build up a distribution of this so that you can use different cluster defining thresholds and still be able to determine whether it's going to be significant at an alpha level of 0.05 or not. And you'll see what that looks like in just a second. Just to give you a little preview, once we've done this, we've used this 3D +sim option and 3D t-test ++. So for example, I can set my voxel-wise cluster-defining p-threshold of 0.01 down here. This is the AFNI viewer. Open up the Clusterize tab, and these will already be input into this statistical data set. So as you move the threshold up and down to whatever kind of cluster-defining threshold you want, it will update the overall false positive rate on the fly over here. So it'll tell you, this particular cluster rate here is significant at 0.001. The two chevrons being 0.001. And so Bob Cox ran a bunch of simulations with this, and he found that across even more liberal cluster defining thresholds like 0.01 or 0.005, you still seem to be at the correct false positive rate. So this is what's recommended these days. One, because it seems to be the most robust, regardless of what cluster defining threshold you want, and across any type of different experimental paradigm, whether it's block or event related. Okay, so with that being said, we're going to go back to our terminal. Excuse me. We're in the residual directory right now. I'm going to ask you to go up one directory. And here are all of the different, excuse me, I'm sorry about that. Here are all the different individual data sets. So for sub 01, sub 02, all the way through subject 26. This was a flanker task, very simple, incongruent minus congruent was the contrast that I was using. Now you'll notice that there are a few different shell scripts right here. I'm going to open up this one, run t-test +sim. And I'm using the VI editor. You can use text editor, whatever you want. We're just going to review what is actually in there. This is a typical 3D t-test script to run a very simple one sample t-test. So within each of these individual subject statistical files, just take it from me, subbrick number 7, this is like a subset of the file, that corresponds to the contrast I'm interested in, which is incongruent minus congruent. Okay. Now you give it a mask. I'm using some variable notation. The mask is this mask group, which only restricts my analysis to the voxels of the brain. And we also have a results directory to write out all of our results. So if you run 3D t-test ++, they should all be pretty familiar. You've had to use all these options before. The only thing you need to add, and this is why it's so easy, just add +sim to it. That's really the only thing. We're not going to edit anything. I'm showing you how this thing is set up. As a side note, for those of you using SPM or FSL, you have your contrast maps. The only thing you need to do is replace each of these files right here with your contrast files. It will still work. It'll still generate a data set that will show you where there are significant clusters using APNI's latest cluster simulation method. Okay. Now, in the interest of time, this thing does take, I'd say, like 10 minutes or so. If you want to, on your own machine, you can go ahead and run this. Since I already have the data output, it's going to throw an error at the very end telling you it can't overwrite it. But just to give you kind of a brief example of what it looks like, if you hit run, it'll start to run these permutation tests down here. Again, it's going to take a long while. I'm going to exit out of this by hitting Control and C. And it's all going to go into this new directory because I have the results that are already been done through clustsim in this directory right here. Test.results clustsim. What I've included, so this is the incongruent minus congruent contrast, the second level result, and also a template that you can overlay this on top of, just for aesthetic purposes. Okay, let me bring this over here. Sorry, I have 2 monitors open, so I have to click and drag everything. So the underlay by default should be the template, and we're going to overlay flanker inc minus con on top of it. I know that the text is a little small. I'm just going to guide you through what I'm doing verbally. On this overlay pane, you see an overlay drop-down menu. I'm going to change that to z-score. And same for threshold as well. Once we do this, we can then set this p threshold. If I right-click right here where p equals 1, you can use a slider if you want to. If you want to set an exact cluster-defining threshold, right-click on the p-value, go to set p-value. Oh, actually, you have an option right here to set p equals 0.001. Right? So this is a typical data set like we would see after we would do the cluster defining threshold. The last part of this is if you click on clusterize. For now, let's just make this 10 because as you'll see in the report, which is now active, it will show you which of these clusters are significant, right? So I use a pretty liberal, cluster threshold at the very end. So obviously some of these are going to be not significant, but it shows you which ones are significant. And you can jump around to the ones that are, say, less than 0.001. So just take a minute, just experiment with this. You can use different thresholding mechanisms here. You can see how it updates on the right this table. And also at the top right here, it tells you, I mean, these have already been calculated for you. It says if you're using, say, whatever the p-value, the uncorrected cluster defining threshold is right here, say 0.02, just by chance, the alpha for the cluster at, say, like the 10% level is going to be 220. For 5%, 394. So there's only a few clusters at this level that seem to pass that threshold. For most people, this may be all you need to do. Again, pretty simple. Now that you understand the principles, how this is done, you should be more comfortable to simply add in +sim to 3D t-test++, and you will get a result like this. All you need to do is set that uncorrected p threshold and then open the clusterized report. So we could end on that note, but there's one more thing I want to point out. And you may have already asked yourself, well, okay, but isn't that a problem if I'm just kind of scrolling up and down on this and only selecting the ones that I want? Okay, we can't read your mind. We don't know what you had in mind beforehand. If you wanted to say, set an uncorrected value of 0.001 versus 0.01, right? And again, this can get back into the problem of multiple comparisons. Oops, excuse me. So the last thing I'm going to close with are some problems with 3D +sim and one more alternative that is still in development. It hasn't been completely beta tested yet, but it shows a lot of promise. So there's still a risk of false negatives with 3D +sim, even this latest version, because in some cases, as we saw, the smoothness can vary among different regions, and 3D +sim isn't going to be appropriate for every individual region. It's going to take the average smoothness and use that for its simulations. And like I said, it's also using arbitrary thresholds set by the user. Things like your cluster defining threshold, things like how much smoothness that you used. Wouldn't it be great if you didn't have to worry about these? Excuse me. And that's where a new method called equitable thresholding and clustering comes in. This is new. This is the past couple of years, I think. Bob Cox published either a preprint or a paper about this in 2019. So just like that +sim option, we also have an ETAC option. If you've used FSL's threshold-free cluster enhancement, I'm talking to the hardcore FSL users, to me, this seems very similar, if not identical in concept. Well, let me explain that. So what if we didn't have to set, a strict cluster forming threshold? So what if, in other words, you can give equal weight to really significant but narrow clusters, like clusters that are very strongly significant but have a very small extent, and make that equal to a cluster that is not very significant but very spread out. Think of it as integrating the area of those two to see whether they reach a certain significance threshold. So what you can see down here is, if we're looking at, say, our typical 0.05 level, for example, and we see, a cluster this big, right? That threshold would not detect this lower cluster down here. But these two clusters seem to be connected, and we still want to use information from the nearby cluster. If we had, again, say a very, very narrow spike, but it was very significant, is that equivalent to having something like a cluster that is less significant but more spread out? Or what if you have two kind of intermediate clusters that are connected by voxels that aren't very significant? Should you still be considering that an entire cluster or two separate peaks? What ETAC does is it makes no parametric assumptions about the shape of the smoothness. Sorry, there's a typo there. And it balances the extent and the height thresholds at a constant false positive rate. So if we're working with a false positive rate of 0.05, right, typically what you would see is you would have this FPR curve, false positive rate curve. And if we set a certain threshold, like a cluster defining threshold right here, we would only detect clusters in this gray rectangle region. Whereas actually, okay, we could have like a very small cluster, but very significant over here, and a very large cluster, but kind of a lower cluster defining threshold over here, which actually should still pass a false positive rate. It's only because we're using such kind of binary yes or no, it's either passing this cluster defining threshold of 0.01 or it's not, that we're going to miss some of these other clusters. And obviously we have clusters which won't pass the false positive rate no matter what we do. So ETAC is going to generate a new curve. It's going to, as best it can, try to kind of create a smoother curve of different, say, cluster defining thresholds. And then we can capture a wider area and find more clusters. So this will account for the problem we have with false negatives. Okay, so this is the last thing that we're going to do today. I think we're still on time here. And again, I have another script right here, run t-test ETAC. Use this as a template. And you'll see the only thing I've changed here is instead of 3D custom, we have ETAC. Everything else is the exact same, and you can use this with either FSL data or SPM data. Now, unfortunately, this also takes a long time. We can't do the whole thing, but we do have the results already output here in this results directory. We're going to focus on this particular data set right here. So open up the APNI viewer. Give me a second to pull all this over here. This is our template, again, just for aesthetic purposes. And this one, TT new default ETAC, global, two-sided, 5%. Again, it kind of looks similar to that cluster corrected image that we had with 3D t-test++ with the cluster sim option. What you have here are, say it has a cluster defining threshold of 0.01. It's going to account for many different, say, clusters that still pass this false positive rate of 0.05. So notice that you can't really change anything through this slider. These are all clusters that's determined to have passed the false positive rate of 5%. Again, just kind of an arbitrary cluster size just to free up the report. And again, you can jump to these different clusters and use this new method if you want to also control for your false negatives. This is still in development. It's not 100% tested. There hasn't been a paper published on it, validating it yet, but it seems to be in the same vein as FSL's threshold-free cluster enhancement. So I hope these scripts are useful. Again, use them as templates, play around with them, run them and see how they kind of go through the different permutations. I'll be sending out links to things like that animation I showed about cluster correction. I'll also give you my slides, and I'll give you the book chapter that has kind of like a more systematic expository text on what cluster thresholding is, how it deals with false positives, and a brief review of the Equitable paper. So thank you for your time. At this point, we have about 15 minutes for questions, or we can go into the Slack channel. So thank you. Oh, there's a didn't know about those.
Right, and thank you, Andy. That was super helpful. Before others get into questions, I just had a quick one about the ClusSim option for 3D t-test that you mentioned. Is that available to other programs like 3D MVM or 3D LME, or is it really just the t-test?
It's only for t-test right now. Again, this is something that they're still working on. Yeah, for more complicated modeling, they do want it to. They do want to apply it to that as well. But as far as I know, it's only with 3D t-test plus.
And so what would you recommend to do in a situation where you have run one of those other programs?
If you have access to the residuals from the first levels, you can still use that kind of older method that I was pointing out, where you estimate the smoothness of the residuals not fit by the model, and then just average those across all the subjects. And you should still get a pretty consistent false positive rate.
Okay, great. Thank you.
Yeah. I haven't used LME in a while. Does it still generate error time series if you want to?
I'm not 100% sure on that. I've only used it a handful. I typically use MVM.
Okay, yeah.
I think it might, but I'm not sure.
Yeah. There should be a way to just whatever's not fit by the model, just use that with 3D full with half max, average those parameters across all the subjects, run 3D ClusSim. But keep in mind that according to their papers, you should use a cluster defining threshold of 0.001 for it to be valid. But it will be valid, is the point. Yeah.
Okay. Are there any other questions out there? Feel free to unmute yourself or put in the chat.
Okay. Oh, here we go.
Oh, look.
Oh, sorry. Do you want to read it?
Oh, no, go ahead.
You were working with brick format. This also works with NII. Yes, absolutely. Yeah, like I said, FSL, SPM, they output by default in NII, and you can make Affinity do that as well. It will work. Okay, a couple more. Could you give an example of what SPM file exactly we would read into 3D t-test? Yes, once you've run a first level analysis, you have those con files, right? So you click on the results button, you specify your contrast, and it generates a con file. These are the same files that in concept I was doing with 3D t-test plus. So, I took a contrast of incongruent minus congruent. If you do that in SPM, it generates a con file, and just put that into where I had my stats files. From Xenia, is there any reason not to use non-parametric tests for neuroimaging studies? Some people have, let me make sure that I'm remembering this correctly. If you have a relatively small sample, like 20, non-parametric tests can be, I want to say that they can tend to give false negatives. I need to double check that, but there are certain cases in which non-parametric is not completely perfect because it needs quite a bit of different subjects in order to build up what looks like a valid distribution. And aside from that, this isn't too much of a problem anymore, but typically you would want to run, say, at least, I would say 10,000 permutations to generate a nice distribution. This isn't that big of a deal for most computers these days. If you have a more complicated model, it can take quite a bit of time, but I don't see that as a major barrier that it was, say, 5 years ago. Okay, from Anna, is there, and Xenia, if I remember, feel free to email me. I'll try to find that reference about the false negative rate with non-parametric. From Anna, is there a reason why the custom options on 3D t-test ++ works only with more than 14 subjects? Again, I think that gets into what I was just saying, that when you're using that, it is running permutations. It's flipping the sign, trying to build up a distribution. And you need a certain number of subjects for that to build up a valid distribution. So I think that's their lower limit, or what they've